Food's good. Okay, so good morning, and I'm going to talk about our work on a technique trying to remove or to mitigate the access pattern leakage. And our techniques is the so-called Scramble and compute. And this is a joint work with our colleges as NUS, the National University of Singapore. Okay, so let me just quickly come through the problem. The problem is that you have a large data set, and now you want to protect it, and then you encrypt every single items on the large data set. And on one hand, you want efficiency, so you don't want to encrypt it using homomorphic encryptions. You want to encrypt it using something small, something very you want to encrypt it only using conventional encryptions. But the downside of conventional encryption is that you cannot perform encrypted domain processing. That means you cannot directly compute on the encrypted data. Then you have to decrypt it in order to compute it. So the setting that we'll look into is that we have a bounded private memory, a very small protected memory. We don't care about how you protect that thing. There's a lot of techniques to protect that private memory. Like you can look into TPM, Intel SGX, Trust Zone on ARM. But the setting we focus on in the abstract level is that you have a small private memory where no one can look into that, and you have a big storage where the encrypted data would sit. Now you can imagine that in order to perform the computation, you would pull the data from the storage into your private memory, and then you decrypt it. You perform the computation on plain text so that it's very efficient. And whenever you write from that private memory to the external storage, you re-encrypt the data. So the adversary cannot see anything within your private memory, but they can see the access pattern, the sequence of read and write, and the order of read and write that your private memory pull the data in. Right? So you can think of this model as an external memory computation. The only difference is that now your RAM is protected and the adversary cannot see your RAM. So everything is good, but only one thing, there's only one downside, that the access pattern would leak the sensitive information of your data. And I would illustrate it via a very simple example. So now you consider that you have two sorted subarray, each of them contain two elements. And this is a toy example, so I have the private memory here, have only two records, right? So the first thing it would do in merging is that you pull the first record of each of the subarray into your private memory, and then you decrypt it. So by the dark side like this, I mean, it's encrypted and it sits in the external storage, and here is a decrypted or is a plain text, and this is a box that the adversary cannot see. So now the adversary see that you, the trusted memory pull the first records of each of the subarray, write something out. It doesn't know the content of the item got written out because you already encrypt that. But it could see that the third element you pull in is from the first subarray. And as soon as it sees this, it can give out a conclusion that, okay, I would see that the first subarray contain the smallest element. So now you could see that even though it cannot read the content of the data, but it can infer something about that. And this scenario is very serious when you have data from multiple sources, and then you use this sensitive data to identify the sources, right? So in existing work, there are like many effort trying to address this, and we can categorize them into two big extremes. One is ORAM, the so-called oblivious RAM, if you ever heard of that. Basically, it's a very generic technique. It's a black box, and then you have whatsoever computation you have, you apply on top of that black box, and it will solve the problem. It is generic, but it would incur the overhead of at least log n per each access. So if you imagine an algorithm, let's say sort algorithm, you have n log n, you apply it on top of ORAM, you could have n log square root of n, right? N log square of n, yeah. Then the other category is that now you don't want something to be very generic. You design a particular special algorithm for your own application. Let's say I design an oblivious sort algorithm. An oblivious algorithm is something that would incur exactly the same behavior on all input of the same size. So you could think of purple sort as a data oblivious, where merge source is not data oblivious. The good thing about that is that it's more efficient than ORAM because it categorize, it cater for your particular problem at hand. But the downside of that is that for every new application, you have to design a new algorithm. And it's quite complex as far as I trying to understand an already existing oblivious algorithm. It takes me days. And I could imagine how much effort it takes to come up with that thing. And because of the complexity, it might be the problem for implementation and vetting of the TCB. Because if your TCB contains some bug or some vulnerability, the security of your entire system is gone, right? So our technique, our work trying to look into the middle of the two extremes. We want to have a mechanism that supports a large majority of the algorithm. We do not try to support every single algorithm out there, but we want to support an expressive class of that so as to reduce a state-of-the-art external memory algorithm. So we just get whatsoever there, and we fit in our framework. If it's applicable, then we just make it there. And we want it to be simple so that it's very easy to implement and it's very easy to understand and it's very easy to vet the TCP. And at the same time, we want the overhead to be very small. And it turned out that the technique is extremely simple. What you want to do is that you get the input, you scramble it in a sense that the correspondence between the input and the output of the scrambling process is hidden. And then you apply the original algorithm on the scrambled data, right? It's very, very simple. You get the input, you scramble it, and then you process the scrambled data. And with a large majority of algorithm, the output of the algorithm applied on the original input and on the scrambled data will somehow be the same. So you imagine sorting. Now I give you 1, 2, 3, 4, and 4, 3, 2, 1. I tell you to sort that thing, you would always get the same result, right? So this is a very simple technique, and we achieved the first purpose with simplicity and very simple. But the only problem is that, as I said, it cannot apply for every single algorithm. It can apply for some algorithm, and it cannot apply for some other algorithm. So what we do is that we give our theorem and we prove it that what is the condition, the sufficient condition for the algorithm on which our technique can apply. And the formalization of that is a little bit convoluted, and please refer to the paper if you want to really understand that. Now we just basically, the definition, the sufficient condition is just two things. First, you can define a tagging algorithm, and second of all, you can define an imitator. If you can do this on the algorithm that you have at hand, then it is for sure that our framework can apply on that algorithm. And by applying on that algorithm, you basically just scramble the data and then apply the original algorithm on the scrambled data, right? So I will come to that later on, but we investigate and we saw that this kind of scope is expressive enough. It covers all computation supported by Spark. Spark is a distributed computation platform, and it's to support most of the data processing algorithm. So just give you an example on how the thing works. I just I forgot. So the scrambling the part, you have to do it in a sense that you do not review the correspondence or the linkability between the original input records and the scrambled data. And fortunately, we have the so-called Melbourne shuffle algorithm, which run in ON, very efficient. It runs in ON, and it requires the private memory of O square root of n. So you could see that if you run the scramble algorithm in ON, then basically you add the additive overhead of ON in the execution. So imagine you have a sorting algorithm with n log n, and then you add this scramble part ON, the overall algorithm, now privacy preserving. That means you solve the leakage via a set pattern, and the complexity is still ON log n. And if you look into data oblivious literature, it takes them years, like several years, in order to have a one data oblivious algorithm for sorting with running in ON log n. But the constant factor is still huge, right? So this is an example. You have the data there. You pre-process it a bit. The reason why you have to pre-process it is because the subtlety. Yeah. But basically, you just scramble that. You apply the original algorithm on the scramble data, and you could see that because this algorithm you apply on the scramble data is the thing that is not privacy preserving. So you could observe something here, and you could observe some sensitive information about the scramble data. But the trick is now, because of the scrambling previously, you perform in a way that there's no linkability between the scramble data and the input. So whatsoever you observe at this part cannot be linked back to this part. So that's why we can solve this. Basically, we make this observation become useless. So that's how we protect privacy via leakage, via access pattern. And to make a comparison between our technique and ORAM and data oblivious algorithm, I already showed that ours is ON, additive overhead, where ORAM is at least log n per x access. And the tailor-made algorithm, data oblivious algorithm, even though they have the same complexity as us, as ours, but the actual running time is significantly higher. We will show it. I will show it in the next slide. Regarding the expressiveness, ORAM cover all applications. Ours cover a set of applications, a class of applications, and we claim it to be expressive. If you take a look at that, it supports all Spark and a majority of data processing operations. For tailor-made algorithm, you have to design new oblivious algorithm for every single application you have. For ORAM, depends on which scheme you use and how familiar you feel about that. I will rate the design and understandability from moderate to complicated, where ours is quite simple. And tailor-made algorithm is also very complicated. And this is the running time, so the detail of the experiment we see in the paper. But basically, I just want to highlight that our algorithm is like several times better than the oblivious algorithm. The tailor-made one is up to 4.1 times better. We don't make the comparison between the tailor-made algorithm and the ORAM because it's obvious that ORAM performs worse in terms of efficiencies. And the better thing is that our framework support parallelism, sorry for the pronunciation, where data oblivious algorithm cannot do so. At least it's not trivial to multi-thread a existing known data oblivious algorithm for a majority of applications, where ours we can support parallelism. So you can see that it could be scalable. So in conclusion, we claim that our framework, first of all, is expressive enough to be useful. Second of all, it's incur low overhead, and we prove it via a complexity analysis and experimental study. And we also show that it's quite simple, and because of all the attributes, we claim that it could support or enable privacy-preserving computation as ease and as scale. And with that, I conclude my talk. Thank you very much.